Hey everyone, here is a quick example of linearization to try to make it super clear to you guys what is really what you're expected to know regarding this approximation to a function, a technique that's pretty powerful, used very commonly to make life a little bit easier. A line can approximate any function if you get zoomed in close enough. That's what local linearity is all about. Okay, so our example here is the arctangent of x, more commonly known as the inverse tangent of x now. We want to know what is the approximation when we're near the point 1 comma pi over 4. If you're just told x equals 1, you've got to plug it in. The arctangent of 1, well, what angle will give you a tangent ratio that's 1? That's 45 degrees, that's pi over 4 when you're at root 2 over 2 over root 2 over 2. So we have that point, that reference point. So the linearization near this point then is simply taking the derivative. Hopefully you know that. I thought about making this arctangent of 2x. If that was the case, remember that you have to use the chain rule. You take the derivative like this, but then you'd have a 2 up on top because the derivative of 2x would put 2 in. But it just made it a little bit more streamlined to do the graphing without that 2x, so I dropped that. But be prepared for a good use of a chain rule. So when we plug in 1 into our derivative function, we get the slope of that tangent line as being a very simple 1/2. Now we can use point-slope form to get that linearization. And point-slope form, then, if we just move the y-coordinate over, we get a more familiar formula that's given to us in our text, that your approximation y then is going to be that y value with this added. And that's like that differential thing that we were talking about. So the approximation then for 1.1, when we plug it in and take away 1, gives us our linearization with 1/2 times 1/10. That's 1/20th. 1/20th as a decimal is 0.05. So we know whatever pi over 4 is, it'll be plus 0.05 to go out to 1.1. Well, we can kind of assume that the way this works is we've got some way using our abacus and our clay tablets to figure out what the decimal is of pi over 4. We just don't want to have to do that from scratch from the get-go, so we have these approximations that'll save us time and be quite accurate. So we've divined that the pi over 4 amount is in fact 0.7854. And we can then add our 0.05 onto that and get our value. So that would be what? 0.8354 would be our estimated value. I didn't type that in. Let me go to Desmos here and show you what it looks like visually. All right, there's our graph of the arctangent function. Let's see if I can drag this graph over a little bit. Yeah. And then here is our point that we're getting near to. Here is our linearization, and you can see that as we zoom in, it approximates that quite well when we're local. Here is the value when I've added on my 10%, okay? So if we want to see that 1.1 value, I've also graphed that in here. If we want to zoom in, this is the point we're asked to approximate, and we can see that it's really pretty close. This is the true value that our calculator would give us, and this was our estimated value, that 0.78 with the 0.05 added onto it. Okay, so I'll zoom out. So that's the first, really the second part of that question. The last part is, what is the closed interval over which we're within 10%? So what we need is to figure out what's 10% of our 0.7854. Well, that's move the decimal, 0.078. So that's what's happening right here. I've added on 10% because clearly this line, with our original function being visibly concave down, is going to be an overestimate. This green line is always going to be more than the true value, our red line. So I've added on that. If it was concave up, I would be subtracting that amount. I just need to know what is this point here. That's our x value is 0.478, that's in radians, up to 0.1624 in radians. That's quite a wide amount. That's, when you think about it, 1 radian is about 60 degrees, so we're from about 30 degrees to gosh, almost 100 degrees. So from 30 degrees to 100 degrees, we're going to be within 10% of the true value. That's really very, very wide. Not very realistic in the real world. A lot of times it would be only like, we would only tolerate 1% error. And then this, we could add another 0, I guess. And you can see how our range is still pretty significant from here to wherever the purple line intersects my straight green line, about there. So the interval will be narrower, but still fairly wide, maybe 20 degrees or so. This approximation is quite accurate. You guys, if taking a quiz, will not be able to use Desmos, so let's look at it quickly on our calculator. Okay, here I've typed in the same function, inverse tan of x, and then I've typed in the linearization just to save a little bit of time. See if we can see the whole thing. If we go to the graph, whoops, I've got too much turned on here. Let me go back here. I can turn off these things quickly and go down. There we go, turn that off. Oh, hit the equal sign and hit enter, and that'll turn that off. There's our graph. And our point then would be what, over here, 1 and about 0.18. But we can still do this on a calculator. We can zoom in a little bit, or we can just chop off the part we want. So if I go to Window and make the minimum not negative but 0, and the y value not negative but 0, that'll eliminate everything but the first quadrant. I go to my graph, there it is. I go back to my y equals, and I can go and turn that equal sign on. That'll be our linearization. But I want to show you here how to get that, use the calculator to get our interval. This is that 10% amount, okay? So whatever, if you're given a value like to be within 3/100ths, you type in 0.03. 10%, you need to find your y value, then take 10% of it. Now what I'm going to do is I'm going to add on my original function. Well, that's y1, and just to show you that you can do it this way by doing plus, and then instead of typing that all in again, I could just do vars over to y vars and choose function and choose 1, and there it would be. That's kind of a shortcut maybe. If I go to my graph, there it is. Again, I can zoom in, or I can do zoom box, and then there's my little cursor. I just need to bracket this. I think that'll be okay, and then I go down, I open it down, and then I open it across, and I just want to see where that upper function intersects my straight line. Okay, now I'm probably going to get close enough. Maybe I'll go down. All right, and then I hit enter, and hopefully it's not too pixelated. So you should know how to find the intersection point up here and the intersection point down there by doing my second and trace button gets calculate, and then I'll do intersect, hit option 5, and I just need to make sure I've chosen my straight line. Sometimes you have to trace along it. Okay, that's not the one I want. I want the other two, so I go up 1, I hit the up arrow, select enter, and then I go up 2 arrows, and I'm on the line. That's my linearization. And then when I hit enter, it should give me the intersection. Okay, so that's when x is 1.62, which we saw before on Desmos. All right, so you can find the lower one on your own. Have fun practicing. Good luck.